Hello, my name is Kevin, and along with my group members Aaron and Simon, we worked under doctors Oz Amram and Kevin Pedro with FermiLab in machine learning based simulations of particle collisions. We were also assisted by our TA Ian and our intern mentors Owen and Alex. So let's start with our problem setup. For decades, physicists have experimented in looking within the basic elements of atoms to understand the fundamental nature of the universe, leading to the standard model that theorizes what makes up our basic particles and their interactions. The invention of particle accelerators have allowed researchers to make huge advancements in this field of study and test the standard model, which is the overarching goal of particle physics. In the real world, data for these particles are collected in particle colliders, which are collision chambers surrounded by layers of sensors. After colliding particles at very high speeds, sensors, called calorimeters, record measurements of the direction and energy of the flying particles from the collision. This results in a dataset coined as the particle shower. However, another way to obtain particle data is through simulations. Physicists can computationally build simulations of particle collider showers by simulating their energies and directionality as detected in calorimeters based on current knowledge from the standard model theory. Any significant differences between these simulation outputs and experimental collider data can highlight gaps within the standard model theory, which physicists can then update simulations based on new theories to match the phenomena from experimental data. The most current example of this in action is the discovery of the Higgs boson curve in the right side image, but there's always a caveat to building simulations. The biggest limitation of the current methodology, Monte Carlo or MC-based simulations, uses up the vast majority of computational resources. The plot on the right shows a time clock of CPU hours used to conduct ATLAS, an example of a calorimeter simulation project. As you can see, 38% of the CPU hours are used for the actual Monte Carlo simulations, which is shown in blue and outlined in yellow. This then becomes the primary target for optimization as you want to increase the efficiency and speed of generating and running these simulations. This is what our work revolves around. So let's first talk a little bit about the data that we're actually working with. As mentioned before, a calorimeter is essentially an array of sensors within a cylindrical collision chamber. We can divide the cylinder into a series of 3D slices, which are each circular as seen in the bottom right image, which are by the contour with a bunch of colored rectangles. Each rectangle is essentially a chunk of 3D space in the calorimeter that has a sensor responsible for it. The colors here are indicating how much energy that sensor has detected. The brighter the color, the more energy detected. So when we simulate an energy shower, what we really mean is we're generating a series of these circular images which each show the distribution of energy detected. And then we can stack each slice all on top of each other to recreate the full particle shower occurring in the calorimeter. We're currently working with 3 datasets simply named datasets 1, 2, and 3. These datasets for calorimeters ultimately get very large and complex due to all the details in the showers, with dataset 3 being the largest and the most messy. So this is where our approach comes in to efficiently simulate these showers. We want to be first able to understand and simulate what the resulting energy shower looks like. This can actually be retooled as a generative task. Specifically, starting with a given set of initial conditions, we can generate what the simulated shower will look like. Some of the best generative models on the market right now are called diffusion models, and a trained one, as you can see at the bottom, starts with an image of a complete random noise and iteratively denoises it to an image that matches the initial distribution the model was trained on, in this context, a cute dog. There's already been work showing that trained diffusion models on these energy showers can simulate and generate really accurate energy showers for application, and they overall perform better than Monte Carlo simulations. The downside is this generation process is still too slow for us in the real world. So let's talk about a little bit about inference. Once you have a trained diffusion model, we can generate our circular images of the calorimeter. We would denoise from a noisy image on the far left to our properly denoised image of what our shower would look like on the right. But this process can be slow since the images we're working with are very high resolution. As you can imagine, there are potentially thousands of sensors within a calorimeter. There is a way to speed up this process, however, which is through a process called latent diffusion. Latent diffusion operates by wrapping the entire diffusion process within an autoencoder, which is its own neural network, to allow the diffusion process to operate on a smaller latent space. How this works is that the autoencoder allows us to take the original resolution noise image, encode it into a smaller image, which diffusion is then performed rapidly on, and then decoded back to the original resolution to get our final input. Now, as you can imagine, this autoencoder and its accuracy is critical to the diffusion process. This quarter, we've primarily focused on understanding and tuning the hyperparameters of the autoencoder. So let's get into the actual details of these autoencoders. An autoencoder is a neural network used to learn encodings of unlabeled data. So what does that mean? Well, you can kind of see the general idea in this image. There's an encoding step that reduces the dimensionality of the input data from a size of 8 to a latent or compressed representation with a size of 2, and a decoding step that recreates the input data from the latent representation back to a size of 8. However, data shape and size isn't always so clean and easy to work with numbers, which comes to the primary issue with autoencoders, the trade-off between accuracy and compression. An ideal autoencoder could encode some data perfectly down to a very small low-dimensional latent representation. However, the problem is, the more you encode and the more you compress some set of data, the harder it is to reconstruct that data, and that is exactly the trade-off between the accuracy of the reconstruction and compression of the autoencoder. So when you want to tune the hyperparameters of the model, we are essentially looking for a good amount of reconstructability while still having decent compression. All right, so on to our autoencoder results and which hyperparameters we exactly tuned for this quarter. The first hyperparameter of the autoencoder we tried adjusting was the learning rate. The learning rate, essentially, as in its name, is how fast the autoencoder learns to accurately represent the compressed data. A higher learning rate would mean the autoencoder more aggressively changes its weights to fit the compressed data, and a lower learning rate is vice versa. We tested 3 different learning rates, 4 to the power of -3, 4, and 5, on our first data set with differing compression factors, represented by the layers. More layers equals more higher compression to cross-check results. We found from the graph on the left that initially a higher learning rate of 4e-3 in blue gave us the lowest possible validation loss, but when stepping up to a higher compression rates to the graph on the right, a learning rate of 4 times 10 to -4 in orange actually gave us the best results. The next hyperparameter we attempted tuning was the actual compression factors. The net compression of the data is the number in the legend. You'll notice that we have 2 models for a compression factor of 1/8. There are different ways to design models containing similar levels of compression, so we tried a few ways to see how the internals of the autoencoder affected performance. While for dataset 1, differing compression rates seem to result in similar validation losses. But we found that for dataset 2, our validation loss increased as we compressed the data more and more. This was expected, as the more we compress the data, the more detail we lose, so the harder it is to recreate accurately. The third hyperparameter we attempted tuning was batch size. Batch size affects how much data we feed to the autoencoder at once. Tuning this parameter would allow us to work on the efficiency of the autoencoder, whereas learning rate and compression factor would focus on the accuracy. The first row lists the sampling time for a model with no compression, which is basically the same as a standard diffusion model. The rest involve compression, making them latent diffusion models. Note that there is a jump in sampling time each time we significantly increase the number of batching events from 100 to 500 and from 500 to 5000. This indicates that there is an optimal batch size to target dataset and compression factor. We also seem to be hitting a lower bound for sampling time due to the computational overhead even for the sampling of a single event. Nonetheless, comparing the first row to the rest, batching allows us to increase sample speed by up to 10 times for compressed data. So ultimately, we have good news with our hyperparameter tuning. In these graphs, we compare the distributions of our diffusion models in blue to the benchmark Geant4 models in black. Note that as of last quarter, spring 2024, there are large deviations at lower energies, especially near where the normalized voxel energy is 0. The blue curve doesn't really follow the ideal black curve. However, as of this quarter, our latent diffusion model with tuned parameters is now closely approximating the Geant4 distribution across all voxel energies, with a strong improvement where the voxel energy is 0. So in summary, our ultimate goal was to increase the accuracy and efficiency of our autoencoder through to a latent diffusion pipeline. Through our hyperparameter search, we have provided 1, a learning rate and batch optimized latent diffusion pipeline, 2, refactored training and visualization scripts, 3, an autoencoder trained on dataset 3, and 4, a full pipeline capable of accurate sampling while maintaining a reasonable sampling speed. And of course, always, thank you for listening.